The James Webb Space Telescope, JWST, often regarded as the successor to the Hubble Space Telescope, has dramatically altered how we interpret the cosmos since its launch. This remarkable instrument has provided an unprecedented view of the universe, revealing mysteries and uncovering phenomena once unimaginable. With its advanced technology, the JWST has enabled scientists to examine the farthest corners of space, exploring galaxies, stars, and planetary systems that formed billions of years ago. This article delves into the various facets of the JWST, from its technological marvels to its groundbreaking discoveries, and discusses how it has transformed our perception of the universe. To understand the importance of the JWST, it's helpful to reflect on its precursor, the Hubble Space Telescope, which was launched in 1990. Hubble allowed astronomers to capture some of the first clear images of distant galaxies, nebulae, and stars, unobstructed by Earth's atmosphere. Hubble's contributions to scientific knowledge are vast, from determining the expansion rate of the universe to observing the impact of comet Shoemaker-Levy 9 on Jupiter. Its deep-field images, which captured light from galaxies billions of light-years away, provided a glimpse into the early stages of the universe. Despite its successes, Hubble faced certain limitations. Its primary mirror, with a 2.4-meter diameter, restricted its light-gathering capacity, and its instruments were designed primarily for ultraviolet, visible, and near-infrared wavelengths. As researchers pushed the boundaries of knowledge, it became apparent that a new telescope was needed, one capable of observing in the infrared spectrum, which would allow it to peer through cosmic dust clouds and study the earliest galaxies. The concept of the James Webb Space Telescope began to take shape in the mid-1990s, even before Hubble had reached its full potential. Named after James E. Webb, NASA's administrator during the Apollo missions, the JWST was conceived as the next major observatory designed to look further back in time than Hubble, capturing light from the first stars and galaxies that emerged after the Big Bang. The design of the JWST presented enormous engineering challenges. Unlike Hubble, which orbits Earth at an altitude of approximately 570 kilometers, the JWST would be positioned at the second Lagrange point, L2, about 1.5 million kilometers from Earth. This location offers a stable environment with minimal interference from Earth's heat and light, but it also means the telescope cannot be serviced or repaired by astronauts. To observe distant and faint objects, the JWST required a much larger mirror than Hubble's. The solution was a segmented mirror made up of 18 hexagonal, gold-coated pieces, giving the telescope a total diameter of 6.5 meters. This mirror had to be folded to fit into the Ariane 5 rocket and only deployed once the telescope arrived at its destination. The JWST also needed a sunshield to protect its instruments from the heat and light of the Sun, Earth, and Moon, maintaining its operating temperature just a few degrees above absolute zero. The sunshield, about the size of a tennis court, is made from 5 layers of captain, a material capable of enduring extreme temperatures. After years of planning, delays, and budget overruns, the JWST was finally launched on December 25, 2021. The launch was a historic occasion, witnessed by scientists and space enthusiasts around the globe. The Ariane 5 rocket carried the telescope into space, and over the next month, the JWST undertook a complicated, carefully orchestrated series of steps. The sunshield was the first major component to deploy, a procedure involving numerous systems and thousands of parts working in perfect synchronization. Any malfunction at this stage could have compromised the entire mission. Once the sunshield was successfully deployed, the mirror segments began to unfold and align with one another. This process took several months, as each segment had to be adjusted with nanometer precision. By mid-2022, the JWST had completed its deployment and calibration, and its instruments were ready to begin collecting data. The initial images released to the public were nothing short of spectacular. The telescope's infrared capabilities allowed it to observe the universe in an entirely new way, capturing astonishing clarity and detail. One of the JWST's primary objectives is to observe the earliest galaxies that formed after the Big Bang billions of years ago. These galaxies are so distant that their light has been redshifted into the infrared range due to the universe's expansion. While Hubble could detect these remote objects, the the JWST's infrared capabilities enabled it to examine them with remarkable detail. In its first year of operation, the JWST made several remarkable discoveries. One of the most significant was the identification of galaxies that existed only a few 100 million years after the Big Bang. These galaxies appeared far more developed and larger than previously anticipated, challenging existing theories of galaxy formation and growth. Scientists had assumed that the first galaxies were small and gradually grew through mergers with other galaxies. However, the JWST's observations indicate that some galaxies formed more quickly and grew larger much sooner than expected. This discovery has prompted cosmologists to revisit their models of galaxy formation and evolution. The JWST also captured images of massive structures that had never been seen before. For instance, the telescope observed the complex network of the cosmic web, an immense network of filaments that connects galaxies throughout the universe. These filaments, composed of dark matter and gas, serve as the scaffolding on which galaxies develop and evolve. The JWST's observations of the cosmic web have provided new insights into the universe's large-scale structure and the role of dark matter in shaping it. The JWST has also revolutionized our understanding of star formation and stellar evolution. Stars are born in dense clouds of gas and dust that block visible light, but infrared light can penetrate these clouds, allowing the JWST to study the birth of stars with unprecedented clarity. One of the telescope's first targets was the Orion Nebula, a stellar nursery located about 1,344 light-years from Earth. The JWST's images revealed numerous young stars, some of which were still encased in their birth clouds. These observations have provided new insights into the processes that govern star formation and evolution, as well as the mechanisms that lead to the creation of planetary systems. The JWST has also observed the final stages of stellar evolution, capturing breathtaking images of dying stars and the nebulae they produce. These observations have illuminated the processes that govern a star's demise, including the formation of white dwarfs, neutron stars, and black holes. One of the most exciting aspects of the JWST mission is its ability to study exoplanets, planets that orbit stars outside our solar system. The telescope's instruments can analyze the atmospheres of these distant worlds, searching for signs of habitability and even life. In its first year of operations, the JWST made several key discoveries regarding exoplanets. One notable find was LHS 475b, an exoplanet located about 41 light-years from Earth. This planet is roughly the same size as Earth and completes an orbit around its star in just 2 days. The JWST's observations revealed that LHS 475b has a thick atmosphere, possibly composed of water vapor, carbon dioxide, or methane. The JWST has also observed other exoplanets with varying atmospheric conditions. Some of these planets possess thick, hazy atmospheres rich in methane and other hydrocarbons, while others have clear atmospheres dominated by hydrogen and helium. These findings provide valuable information about the diversity of planetary systems and the conditions that might support life. One of the most compelling questions in cosmology is whether life exists elsewhere in the universe. Although the JWST cannot directly detect life, it can search for biosignatures, chemical indicators that could suggest the presence of biological activity. For example, the detection of oxygen or methane in an exoplanet's atmosphere could imply the existence of life processes. The JWST's ability to study exoplanets opens a new chapter in the search for life beyond Earth. As the telescope continues to explore more planets, it will provide vital data that could answer the age-old question: are we alone in the cosmos? In addition to exploring distant galaxies and exoplanets, the JWST has captured some of the most beautiful and mysterious objects in the universe. One such example is the Tarantula Nebula, a vast star-forming region located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. The Tarantula Nebula, also known as 30 Doradus, is a vast expanse of gas and dust where thousands of new stars are forming. The JWST's images of this region show intricate filaments of gas, glowing clusters of young stars, and the remnants of supernovae. These observations have offered new insights into the processes that drive star formation and the life cycles of massive stars. The The JWST has also captured stunning images of nebulae, such as the Eagle Nebula and the Pillars of Creation, unveiling details that were previously obscured. These images have not only mesmerized the public, but also provided invaluable data for astronomers studying the birth and death of stars. While the JWST has achieved tremendous success, its journey has not been without its challenges and controversies. The telescope's development was marred by delays and escalating costs, with the final price tag nearing $10 billion, substantially higher than initial estimates. These issues sparked debates among scientists and policymakers regarding the feasibility and worth of the project. Some critics argued that the resources devoted to the JWST could have been better spent on other scientific pursuits, while others contended that the telescope's potential for transformative discoveries justified the investment. The James Webb Space Telescope is not only a scientific undertaking but a monumental human achievement that transcends borders and generations. Its discoveries are already reshaping textbooks and broadening our understanding of the universe. But its full impact will unfold over the coming decades. As the JWST continues its exploration, it will undoubtedly make even more profound discoveries, expanding the boundaries of human knowledge and inspiring future generations to reach for the stars. The JWST represents an extraordinary leap forward in cosmology, not only because of its cutting-edge technology, but also because of the novel questions it raises about the universe. As the mission progresses, the JWST is poised to deepen our understanding of cosmic phenomena in ways that were once inconceivable.